All right, let's take a look at the warm-up. All right, so the warm-up has us just finding the values of x to solve the equations. Essentially, we're finding the roots here of some polynomials. So when I look at the first one, my first step might be to try to factor that. I should be able to factor that into what and what? X minus 5, x plus 1. And then I can see that the values of x are x equals 5 and x equals negative 1. I look at the next one. That one factors into what? X plus 3 squared. And so my roots would be negative 3 and, well, negative 3. I have a repeated root. And then for number 3, the easiest way to think of that one is to maybe add the 4 to the other side. X squared equals 4. Take the square root. I'll get x is equal to plus or minus 2. And the last one, same idea, except now maybe I'll subtract 4 to the other side. Ooh, now what are my roots? Plus or minus 2i. Right, you might look at it and say, well, there are no roots. You can't factor that. There aren't any real roots, but we do have complex roots. That would be plus or minus 2i. Any questions from the warm-up? All right. All right, plan for today. Exams will be graded by next Tuesday. It's a big stack, so I'm just powering through them. So hopefully by next Tuesday, there should be plenty of time to get them done. We'll get them back to you then. Any questions about the exam? I know it's hard to comment about content until you get your score back, but was the proctoring okay? I hate not to be here when the exam actually runs. How was the time? Was the time reasonable? Yeah. Okay. Once you get them back, any feedback is always good. I always appreciate that. So once again, class has started now, so make sure your phones are away and all that good stuff. I will, however, start off this class with a little bit of an advertisement. As you know, I run the Math Lab here. The Math Lab is hiring. So you guys are ideal candidates. If you've already been through Calc 3 and are going through this course, you're an ideal candidate for the lab. So I encourage you maybe to look into that if you're interested. Pay starts around $10-20, I think. There are some positions that get up to a little bit $13 though. So those things that get paid to practice math and Mathematica. Not all about studying and grading and doing other stuff. We do some other interesting things in the lab. For instance, yesterday, I ran this command, pulling Wolfram's logo here with one line, and then with one more line, just exporting that to an STL file, and then we brought that to the room next to the lab. I literally pay one consultant just to play with the 3D printer all day yesterday. So there are some other opportunities other than just writing and grading labs. So if you're interested, stop up to the Math Lab and apply. They have applications up there. Any questions? All right. All right, on to chapter 2. So the rest of the textbook is now published online and got sent out. So hopefully you had a chance to read through 2.1, preparation for today. The big idea as you started that reading was the higher they are, the harder our problem gets. We look at higher order differential equations, and they are harder than our first order. Not surprising. The other comment that was made was that it's easier if it's linear. Nonlinear makes it harder as well. So we're going to focus on linear higher order differential equations. But one of the differences is that they're still hard. When we were working on first order differential equations, we said if it's nonlinear, well, we got separation of variables maybe we can tackle it with. Maybe it's exactly that. But if it was a first order linear differential equation, we could solve using that first order technique. Right, we do the integrated factor, and maybe we come out with a nasty integral, but we can basically write out a solution for it. It is not going to be that way for higher order differential equations. Even though they're linear, they still might be very, very hard, if not impossible for us to tackle. So we're going to have to restrict our group a little more even. That was one of the sad points, right? So we're going to look at higher order linear differential equations with constant coefficients. One more restriction to make it a nicer group, because now we'll really be able to generate a process to solve these things. So higher order linear differential equations with constant coefficients. And if you have one of these things, it can be written in this form. And this form, that a sub n minus 1, all those coefficients, those are just constants in this case. Those are not functions of t. Those are the constant coefficients. And then I have a couple examples here of differential equations that would fit into this group that are linear, higher order differential equations with constant coefficients. We see the first one here. One of my coefficients, it's 1, -2, -3, so all constant values. Is it linear? Well, we have a quick check to see if it's linear. We look at all that dependent variable values and see if those things are raised to the first power. If they're raised to other powers, or if they're argument of nonlinear functions, it would not be linear. So we have that kind of quick check. Over here, I have sine of t. Is that a problem? No, that's the independent variable, so we don't care that guy is there. But once again, just to kind of refresh from first order, why is that called linear, and how can we actually prove that it's linear? Well, the idea is that we can define an operator. Here's my operator L. And I'm going to define my operator to be d squared minus 2d minus 3, where d is the derivative operator. If I say d of something, it means it takes the derivative of that thing. I could then look at L of x. This is me applying my operator to some function x. And the result would be, here's my operator. And I'd be applying it to x. It'd basically be taking the d squared, applying it to x, minus the 2d, applying it to x, minus the 3, applying it to x. And then what is this guy? Well, that's just x double prime. That's just 2x prime. That's just 3x. So when I define this operator this way, my differential equation can be expressed as L of x equals f of t in general. Any function of t could be on the right there. But in my specific case, I just have a 0 over there. And the big idea is that the differential equation is linear if L is linear. Okay. So I can rewrite the differential equation in terms of an operator. If the operator is linear, the differential equation is linear. We do that because we have a process for determining if an operator is linear. And now we can use that to extend the idea of linearity to the differential equation. Is the operator linear? Well, we've got to do this thing. We got to check to see, hopefully that guy is eventually going to look like this. That's the goal. And then also we could check to see if the operator applied to a constant times x is equal to, hopefully, a constant times the operator of x. Those are the two properties of linearity. So we can show those things are true for this operator, then it's definitely linear. And once again, we have kind of our quick check. But I do want to go through this one more time as this bigger process just to verify something here. So what does this mean? Well, once again, my operator's up here. We've seen how it was applied before. I'll basically left us with this case. If I apply that to the sum of two functions, I would basically get this applied to both x and y, minus 2d applied to x and y, minus 3 applied to x and y. And then I look to see how that d squared can be applied to x and y. How does the derivative? Well, I have that property of derivatives. The derivative of sum is the sum of the derivatives. So in this case, this can directly be written as x double prime plus y double prime. Right, same thing with the first derivative. So this basically turns into minus 2x prime minus 2y prime. And then the 3 multiplication distributes over addition. So I can rewrite that as, oops, this is a y, as minus 3x minus 3y. And then lastly, I would just rewrite this, grouping the x terms and grouping the y terms. And this, I can see, is L of x, and this is L of y. Okay. Now, if my original differential equation had like x double prime minus the quantity 2x prime squared, that would be a problem. If I went through the same process, I would get this quantity because this middle term is going to be kicked out based on the square. This will only work if the equation originally is linear. And we can do the same thing to verify the other property. But I'm guessing at this point you'll take my word that that one's also true, right? Okay, so I'm just showing that it is linear, right? All right. Now, when working with a linear differential equation, it can be expressed then in this new form in general. We have a little vocab here. The differential equation is homogeneous if that f of t thing is 0. If I can express that as L of x equals 0, that is a homogeneous equation. And if I can't, if there's some non-trivial function f of t over here, then it's inhomogeneous. And I know you just love new vocab, right? And they're like, yay, more definitions. Right? But we really do give you this for a reason. The idea is that this inhomogeneous problem is going to be hard to solve. And what we're going to find out is to find a solution for that, we're basically going to have to start off with the homogeneous problem. We'll find a solution for that thing, and then we'll build on it to get the solution to the inhomogeneous. So you really do need to separate the two types of equations. Any questions so far? All right. The big stress about linearity is because we're about to tie differential equations strongly to linear algebra, right? And so we're going to review a couple linear algebra ideas, but I really want you to try to make that connection. And so we're going to try to use that vocabulary a little bit here. All right. Homogeneous linear equations have special properties. If x1 and x2 are solutions to that equation, then some constant times the first solution plus some constant times the second solution is also a solution to the equation. Now you'll see in your engineering courses, this property used in physics as well is used quite a bit. It's called the superposition principle. It's kind of like its applied name. And we have the property and we can write it out, but I really want you to kind of feel what this thing means. I have a solution, or I have a differential equation, very specific example, x double prime minus 2x prime minus 3x equals 0. Differential equation. And I am telling you that these are two solutions. And how would we verify that? Well, if I wanted to check to see if the first one was a solution, I would have to plug it in and see if I get a true statement. So I could take the derivative of x1, the second derivative, bring it over here, plug it into the differential equation, and I better get some sort of equality statement. I better get 0 equals 0 and not 4 equals 2 or something, right? If I can plug it in and get a true statement, I can verify it's a solution. But what I want you to do is now look at this guy. Look at x3 equal to 2e to the negative 2 plus 3e to the 3t. And say, is this guy a solution? Now we kind of can say yes because of the theorem above, but I want you to show me. So go look at x3 and figure out, does the second derivative of x3 minus 2 times the derivative of x3 minus 3 times x3, does that thing really equal to 0? Go ahead and take those derivatives, throw them in. You should really check this because it's so weird. I just don't any number of functions, put them together and still get that. take those derivatives. Actually write them out. Practice to go through the mechanics. All right, I calculated my derivatives. I threw them into my differential equation where they belonged. Now I'll clean things up a little bit. I got 2e to the negative t, 27e to the 3t, distribute my negative 2, get plus 4e to the negative t, minus 18e to the 3t, distribute my negative 3. Looks like I'll get this stuff. Hoping that's equal to 0 somehow. Now I'm going to do a quick grouping. I'm going to get all my e to the negative t pieces. Right, I got 2 of them right here. I got 4 of them there, and negative 6 of them there. And then I'll gather up all my e to the 3t pieces. Looks like I got 27 there. I got negative 18 here, negative 9 there. Looks like it is equal to 0, right? Yay! Right. Once again, it's kind of a non-trivial idea, though. Any multiple of either of these solutions can come together to form the general solution. In fact, it turns out the whole family of solutions, all of the solutions now, can really be represented like this. C1 times the first solution plus C2 times the second solution. And we talked a little bit about it in our current differential equation. That's a second order differential equation. And so sometimes I expect to have 2 constants in my general solution. I only have those constants here. So this is one way I can represent all of the solutions. In fact, more generally, if you have any second order homogeneous linear differential equation with constant coefficients, right, ax double prime plus bx prime plus cx equals 0, I can always express my solution like this. Constant times some solution plus some other constant times some other solution. Or x1, x2 are 2 linearly independent solutions to my differential equation. That's great. That's a way that I can find the whole solution family. All it is a linear combination of these 2 other pieces. I just said the vocabulary. I want to stress it again. When you talk about some constant times one thing plus some constant times another thing, the linear algebra works that as a linear combination of x1 and x2. Okay? So what am I saying here? I'm saying that I'm looking for a whole family of solutions, all of the solutions, the entire solution space, if you will, for this differential equation. And I can find them if I just know 2 solutions. In some sense, these 2 solutions, x1, x2, are the building blocks for this solution space. If you're looking for any other solution, I can find some linear combination of these 2 guys, and will lead you to that specific solution. Okay? Say a bunch of words here. I'm hoping it's jogging your memory a little bit. it should be describing something from linear algebra. What am I trying to describe? Linear space, absolutely, a vector space. This solution space we're talking about for a homogeneous differential equation with linear constant coefficients is actually a vector space. If that's a vector space, then x1, x2 are very specific items as well. Because I can generate the whole space from these two things. What are these two things called? These two special elements of my vector space that can generate the entire space. Basis, absolutely. Spanning set here also is pretty close, a little bit different. But this is a basis for my solution space. Okay? And so I really want you to kind of connect these ideas. When we say that the solutions to this differential equation form a vector space, then I can take all of my theorems, all of my properties from linear algebra, and now apply them to differential equations. And that's a pretty powerful tool. Here's the big idea. I can even extend this to higher dimensions. In general, the set of solutions to an nth order homogeneous differential equation is an n-dimensional vector space. Any solution, and thus all of the solutions, can be written as a linear combination of n basis vectors. And by vectors here, I mean elements of my vector space. And we write them all out like that. And what is this basis? The basis is a set of n linearly independent solutions. And so you can think back to linear algebra and say, oh, I do all this crap. I remember you used to give me two vectors and I had to show whether they were a basis or not a basis. We had to check for independence. We're going to have a similar test here. And it's kind of a review if you're connecting it to the linear algebra. We're going to have to test to see if these two solutions are independent or not, to see if they really form the whole family of solutions. And from a fundamental perspective, the nice thing about this is we know we got them all. I know when I can really generate something that represents the entire space. So I know if I generate this basis, I know the dimensions of the vector space, so I know how many vector bases I need to really cover the whole space. So I know that if I have a third order differential equation, I know what the solution form will look like. Okay. All right. All right. Do we know what they look like? Here we go. So I have some differential equations here. If we want to solve them, what form would the general solution have? I'm gonna get like 120 some, but it's looking a little sparse in the middle here, so not sure. A lot of empty seats today. Prepping for career fair, I'm sure. All right, let's see what we got. Mostly B, a little bit of A and C though. The idea is I see a second order differential equation here, second order, which means my solution form is going to look like B. It's going to be a linear combination of two basis vectors. And number 2. What is the solution to number 2 going to look like? All right, pretty happy with C. I agree with C. I see a third derivative here. This is a third order differential equation. I expect to have 3 terms here. All right, any questions? All right, so all I got to do is find out x1, x2, x3. I just got to find out those solutions. I can pin them all together to form a general solution. So how do we do that? All right, beginning of the textbook said, there are basically 2 ways to solve differential equations. You manipulate the equation until you get a form you can straight integrate. Or you take a guess. We are now at the guess stage. Right? When you guess what the solution looks like, you figure out the details later. Right? Now I hate it when books write that kind of thing. Assume that this is true. Like, where did that come from? Right? In this case, there really is kind of a logical reason to make our assumption. We look at that differential equation as an example. It says take some number times y double prime, some number times y prime, plus some number times y, and somehow you're going to add these guys together to get 0. Okay? And this y is a pretty special function. For instance, if I took y is equal to x to the 4th, what would the derivative be? 3x, 4x cubed. Thank you. Y double prime would be 12x squared, right? Can I take some number times y double prime plus some number times y? Can I add those things together with some constants to make 0? I can't. I can't really combine x to the 4th with x cubed. Can't take 2x cubed and get rid of an x to the 4th. Doesn't work like that. So what this is saying is that whatever that y function is, it has to be a kind of function where the derivatives look kind of like the function. What kind of function is that? Exponential function. Okay, that's where that guess comes from. Because of the way we have to combine these, my solution here has to look like, let me just change these to x's. That's what the book is using here. My solution will have to look like some exponent, exponential function, where I have e to the rt, some number times t. I don't know the right value of r necessarily to make this the function, but I know the solution is going to look something like this. Okay? So does that guess make sense? All right, here's the process then. I want to solve this differential equation. I'm going to assume that my solution looks like that. And if that's the solution, I should be able to plug it into my differential equation and get a true statement. So that's exactly what I do. I calculate x prime, which is going to be what? re to the rt. I calculate x double prime to get what? R squared e to the rt. And then I plug them in. I have r squared e to the rt minus 4 times x prime, so minus 4 times r e to the rt, minus 5 times x, so minus 5 times e to the rt, is supposed to be equal to 0. And now I basically got to solve for r. How do I solve this thing for r? Well, one way I can do it is I can factor out that e to the rt. I'll be left with r squared minus 4r minus 5 equals 0. And then I look at that guy. I say that is the product of two things, and it is equal to 0. The only way the product of two things is equal to 0 is if either the first thing is 0 or the second thing is 0. When is the first thing equal to 0 here? Never, right? It's the exponential function. That guy is never equal to 0. So the only way that this thing is equal to 0 is if this thing is equal to 0. Okay? Now I just have a polynomial. I can figure out the values of r that make this 0. Those must be the right values of r to make my assumption true. This right here is called your auxiliary equation. Take a look at your auxiliary equation. Take a look at your differential equation. You see the similarities here. It's really going to get to the point where you're not going to write down those steps right now. Differential equation, here's my auxiliary equation. But I want burnt in the back of your brain that auxiliary equation was gotten derived by assuming that a solution was e to the rt. That's what we do with r in time. Okay? All right, so I solve this thing. I'm going to factor that into what? R minus 5, r plus 1. So it looks like r is equal to 5, or r is equal to negative 1. So that means one solution must be e to the 5t, and one solution must be e to the negative t. I was able to generate two solutions. Now really the next step is to say, are these solutions linearly independent? Right? Well, to check to see if two things are linearly dependent, we're really just saying, are they multiples of each other? Can I take e to the 5t and multiply it by some number to get e to the negative t? I can't. Right? So if those r values are different, the result will always be linearly independent. So that means my general solution is just going to be some constant times the first solution plus some constant times the second solution. And that is our general solution. So what do? I have my steps on the left. Write down steps that make sense for you, right? I wrote, assume x equals e to the rt is a solution. Plug in the differential equation, solve for r, form solution. If you want to say, write auxiliary equation, solve auxiliary equation, form solution, whatever you want, right? Write something that makes sense to you. Any questions so far? Okay. All right, a little matching. Match the differential equation. Go ahead and write A, B, C, or D for all four problems. And once you get done with all four problems, then enter in your letter. If you have extra time, go ahead and find your work. So you're trying to practice. See if you got it. Don't just sit there. Whatever it takes to get before I get it. All right, so we'll see what we got for number 1. All right, very confident B. Absolutely. So we take our values, we assume that x equals e to the rt, x prime is equal to r e to the rt, x double prime is r squared e to the rt. We plug those values in, we get r squared plus 6r plus 8 equals 0. That is B. Wonderful. Next one. Once again, pretty confident with D. We look at this guy as 6r plus 8 equals 0. Sure enough, that is D. Doesn't have to be a second order or higher. First order will be fine as well. We look at the next one, number 3. We see what we got here. Very confident C. We have 6r double prime, so 6r squared plus 8r equals 0. No constant because there is no x term here. So how are we matching these guys up? This was D here. This was B here. This one we said was, what was it? C. And the last one must be D, right? Sorry, A. Numbers good, letters bad. Okay. All right, so we have those values. All right. So all we're doing is generating that auxiliary equation. Pretty straightforward, not too bad. Now let's give ourselves a little bit of room here. Slide that over here. What do we do with these auxiliary equations? Well, we can actually just go ahead and factor them and find our solutions. If I take that first one, I just factor the equation into r plus 4, r plus 2 equals 0. Be careful. Be careful. So often on quizzes or exams, people write that down and say, oh, r is 4 and r is 2. Right? R is negative 4. R is negative 2. Right? So just be careful. Kind of know the right value, but you got to be careful as you go through it. So what is my solution? My solution is just some constant times e to the negative 4t plus some constant e to the negative 2t. What about the next one? Well, here we just have r is equal to a negative 4/3. I just subtract 8, divide by 6. So that means my solution should be some constant e to the negative 4/3 t plus what? Is just having 1 okay? Why? First order differential equation. I only expect to get one value here. That's fine. Now look at the next one. The next one I might factor into r. Actually, I'll factor into 6r. And I'll be left with r plus 4/3 equals 0. So I have r is equal to 0 and r is equal to negative 4/3. For my solution, it should be c1 e to the 0t, which is just c1, plus c2 e to the negative 4/3 t. Is that okay? Sure, that's absolutely fine. And then lastly, I have this one. This auxiliary equation was 6r squared plus 8 equals 0. I got r squared is equal to negative 4/3. What does that mean? R is equal to plus or minus I times the square root of 4/3. Uh-oh, right? And this is our problem, right? The rest seems pretty straightforward, right? You generate a polynomial, you find the roots, form your solution. Straightforward. Yay, differential equations is easy, right? And there's a problem, always a problem. Here's our problem. The auxiliary equation will give us an nth degree polynomial, right? All we have to find the roots of that polynomial. First problem is we can't always do that analytically, right? You can't find a closed form equation for anything bigger than infinity. Right? Anything 51 or higher, they don't have a closed form solution. You might say, oh, that's crappy, right? But actually, we have other means that look at those rows. We can always approximate those numerically. So I use a numerical technique to approximate the roots of much higher order polynomials. So I have a 10th degree differential equation. I generate a 10th order polynomial. I use some sort of numerical process to find the 10 roots. Boom, I get my solution. I'm all done. But still not too bad. We can still do that. But there's other problems. We also have different ways those roots can come to us. Those roots can come in 3 different forms. What do those forms look like? Well, we can see them all if we just think about the second order case. A second order polynomial looks like a parabola. Here's an example of a parabola. What are the roots of the parabola? That x value, right? That's 2 nice, beautiful roots. But I could certainly shift that guy up and have it look like this. We're just touching the axis at one spot. I only look like I have one root, but that is a repeated root. That one value repeats itself. So I get something like x squared here in this case. Root to be x equals 0 and x equals 0. And then I have this case. It doesn't look like there are any roots. What case is that? Complex roots. Right? We don't have real roots here, but we'll have complex roots. So those are our 3 cases. Right? So depending on the roots of the polynomial, we'll have to form our solution in different ways. All right, what are the different solution forms? My roots look like this. R1, R2, R3, ... These are distinct different values, right? R is 5, then 7, then 0.2, whatever, right? Then it's easy to form my solution. I just do what I've been doing. My solution is just some number, e raised to the first root times t. Some number e to the second root times t. Third root times t. So on and so forth. If I have distinct roots, it's no problem. I just form my solution. What if my roots are r, and then r, and then r, and then r? You know, for example, what if my roots were 2 and then 2? Well, let's just throw those values in there, right? C1 e to the 2t plus C2 e to the 2t. What's the problem? Why can't I just do that? They're not linearly dependent. It's basically the same thing, right? If I actually wrote that down, I could just factor out e to the 2t and say I have C1 plus C2. It's a new constant. Call it C3. I don't really have 2 pieces here. I just have one piece that's, well, repeated, right? I need 2 linearly independent solutions. In the first case, if those are different r values, those functions are linearly independent. But here, e to the 2t is not linearly independent from e to the 2t. So what do I do? Well, what do I do? Well, I take my first solution, and that solution. Then I assume the second solution, some function times that first solution. I take that guy, and plug it into my differential equation. I do a ton of algebra. I have to make some substitution that reduces that second order differential equation to a first order differential equation. And then use a first order differential equation technique to find the solution back then. Back substitute. Boom, I have my second solution. Right? Same process. Turns out I do all that here, and I find out the second solution is t times e to the 2t. And it's always going to be that way when we're dealing with this family of solutions, right? So what is the second solution? It's t times the first solution. What if it was repeated more times? What if it was 2 and 2 and 2 and 2 and so on and so forth? The next one would be t squared e to the 2t. See, 4 times t cubed e to the 2t. I just keep multiplying by t. Once you know, then you don't say, there's a long process that generates a second solution. That's what happens to me. It's not like they say, I have a problem, multiply by 2. There's a process there. But that's what the result is. Okay? So now you know that if you have repeated roots, boom, you just write out your solution, but you have to add factors of t for the different terms. Any questions there? All right. What if we have the root that looks like alpha plus beta I, some complex number, right? 2 plus 3i. What do we do here? Well, once again, what's the problem? Can't I just do some constant e to the 2 plus 3i times t plus some constant e to the 2, should be plus or minus because those roots always come in pairs, minus 3i to the t? Can I just do that? Is that a solution? Is that a basic? Actually, it is. But it's not useful. Right? I want to find the solution here so I can use it, right? So I can find out where this spray is at some specific time or where something's happening. And this is not going to give me a useful form. Like, because that always complex values in it. I said my general solution was any linear combination of two good solutions. So I'm looking at this guy saying I have a linear combination of two good solutions, but maybe I can find a linear combination of two better solutions. That's basically what I'm going to do here. What we do is we say, okay, we have this thing, and we do a bunch of algebra, and we also use the fact that e to the I theta is equal to cosine of theta plus I sine theta. This is Euler's identity, and a super useful and powerful thing that you can actually prove using Calc 2 and Taylor's theorems. Interesting enough, right? But you basically use that guy with a bunch of algebra, and you can rewrite this solution form to look like this. E to the alpha t times C1 cosine of beta t plus C2 sine of beta t. And you basically have the same idea. The solution space defined by the bottom linear combination is actually the same space as described by the above one. I'm just using a better basis, a basis of real values. Okay? And it's, I got sines and cosines, but that's better than imaginary values. Okay? So if I find my roots are this, what do? I just write out my solution. It's e to the 2t times c1 cosine of 3t plus c2 sine of 3t. Once you find the roots, you have to figure out location. And we're going to appropriate solution. Something is a highlight. That is cosine of 3t, not the cosine of 3i. That beta value here, or your book will use beta, is the coefficient to the I term. The imaginary part of the complex number, which the coefficient to that term does not include the I term. There's the real number coefficient here. Any questions here? Okay, you got your three forms. The idea is next time we're going to show how we use that thing to generate this form, and we'll do a whole bunch of practice with solving different equations.